Hello and welcome back. In this video, we're going to look at 4 different ways to simplify the logic of our programs. Always, our programs should be written to be as simple and readable as possible, and this makes programs easier to modify and understand for ourselves and for others who might want to modify and update them in the future. Also, programs that are written simply and clearly are much easier to understand for you and therefore easier to debug and fix, so you can be sure that all the errors in the program have been eliminated, or as confident as possible anyway. So the 4 techniques we'll look at are simplifying logical expressions, and in particular we'll look at De Morgan's rule. We'll look at flattening nested code, because nested code tends to be inherently more complex than flat code. You'll see why shortly. We'll look at introducing temporary boolean variables as a way to squirrel away information to break down and simplify more complex structures. And we'll look at writing boolean valued functions. Okay, so let's get going. De Morgan's theorem is a theorem of logic. It's a basic boolean algebra method that's very useful in computing. And what it says is that if we've got 2 conditions A and B, and we're wanting to determine not the result of A and B, we can rewrite that, if necessary, as not A or not B. The 2 are logically equivalent. And in the next video, I'll briefly introduce truth tables, which allow us to prove these logical equivalences. So, the other of De Morgan's rules is not, brackets, A or B, is the same as not A and not B. So, for example, if you're thinking about the conditions that'll determine whether you go out tonight or not, you might be thinking, I'm not going if it's raining or if I'm feeling tired. Through De Morgan's rule, this is directly equivalent to, I'm not going if it's not raining and I'm not feeling tired. So we could rewrite these statements in pseudocode as if not, brackets, is raining or is tired, go, which is directly equivalent to, probably the simpler version in this case, if not is raining and not is tired, go. So in my opinion, this one's slightly simpler and easier to understand than this one. And often, stylistically, you'll make a determination as a programmer of which of 2 alternatives is easier to understand, and you'll always go for the easier one. De Morgan's theorem just gives you one more alternative for how to simplify your logical structures. As another example of De Morgan's rule, consider the conditions under which we were printing the roots in the quadratic example last time. We might have rewritten or written some pseudocode, something like this. Unless A is 0 or the discriminant is negative, print the roots. With De Morgan's rule, we can rewrite that as if A is non-zero and the discriminant is non-negative, print the roots. So this case is the second example there. If A is not equal to 0 and the discriminant is greater than or equal to 0, print the roots. I think this is much more readable and much easier to understand than the logically equivalent through De Morgan's rule alternative that looks like this: if not, A equals 0 or discriminant is less than 0, print the roots. I find this one harder to understand and this one much simpler. So in general, unless X means if not X. So that's another thing to keep in mind when you're looking to simplify Boolean expressions. Often this is a stylistic choice and it's just a judgment call for you which one seems most simple. What seems more simple to you is likely to seem more simple to others who also need to understand your program. One more point about Booleans before we move on is that Python is what's called a lazy language. So A or B, a Boolean expression A or B, returns true if A is true. If A is true, that's sufficient to determine the truth of A or B. So it doesn't evaluate B if A is true. It only evaluates B, goes on to process the B part of this expression, if A is false. Okay, so knowing that A is true is sufficient to determine the truth of A or B. So because Python is lazy, it doesn't bother evaluating b if a is true. A and b returns false if a is false. Okay? So having determined that a is false, it's impossible for a and b to be true. So it doesn't bother, it's lazy, it doesn't bother to evaluate b. So it evaluates b only if a is true. Hopefully that's clear to you. You can write little programs that test this out. And this can be really important if b has side effects or might generate an error. For example, this is an incomplete piece of code, but hopefully you'll get the idea. If we've got some code that is assuming that somebody doesn't have a second name, so maybe this is a banking application and it's got to deal with normal people who have first and second names, but then there are also people like Prince who only have a first name. So we're going to start by assuming people do not have a second name. And what we're going to do is try to process some data. Maybe we're inputting data from the user. If a name is present in the input data, a second name is present, we'll change the boolean value for has second name to true, and we'll make the assignment to that second name. Okay? But this assignment only happens if the person has a second name. So it's possible to get to the code beyond this conditional statement with has second name being false, and no assignment being made to second name. If that were the case, this following statement, if has second name and second name is Fred, okay, imagine the situation in which no assignment has been made to second name, has second name will be false, and it's impossible for false and something to be true. So because Python's lazy, it'll never get round to looking at the value that's referenced from second name. So our program in this case will be fine. It'll process perfectly okay because it'll never go off and evaluate the second part. Having determined that has second name is false, it doesn't need to do the second part because it's impossible for false and something to be true. But if we wrote that statement in a different way, if second name equals Fred and has second name, in this case it has to look at the first part. It's going to say, okay, well, what value is referenced from second name? And it's going to say, well, hold on, second name hasn't been defined yet, and if you try to look at a value that hasn't been defined, it's going to cause the program to crash. So this lazy short-circuit evaluation is something that can cause risks for you, and you need to understand that Python only evaluates the second half of A or B, only evaluates B, in the condition that A is false. And it only evaluates B in a Boolean expression A and B if A is true. Okay, hopefully that makes sense for you. Another way that we can simplify our programs is by avoiding nested structures to flatten the code. And generally, this will greatly simplify our solutions. So it's not always the case, but it usually makes the programs more readable. For example, our pseudocode for the quadratic example used a nested structure in our previous solution, but we can eliminate that nesting using a pseudocode that looks something like this. We input a, b, and c, we compute the discriminant b squared minus 4ac, and then we have a single flat if, elif, else structure without any nesting that says if a is 0, we print not a quadratic. If the discriminant is negative, we print the roots are imaginary. And otherwise, we compute and print the roots. So have a think briefly about why this might be better or worse than the original. And for me, the substantial improvement is that this is a much simpler algorithm, much simpler solution. It's easier to understand. Possibly the only disadvantage, though, is that we always calculate the discriminant. Previously, here's the Python implementation of our previous version. In the case that a was equal to 0, we didn't bother calculating the discriminant. We never got a chance to do so, so we printed out not a quadratic. Whereas this one is going to calculate the discriminant regardless. And this will take a tiny, minuscule fraction of computing time. So this is marginally less efficient. but that really doesn't matter in most cases unless you're doing scientific computing and you're calculating millions, billions, or trillions of quadratics all at once. So this solution's more efficient, this one's simpler and better in almost all cases. The third of our methods for simplifying Boolean structures is to use temporary Boolean variables. So consider that we're writing a program for a game of chess or similar, where there are 8 rows and 8 columns on the board, and we're writing a piece of code to determine whether those rows and columns are in a legal range, which means they must be in the range 0 through to 7 inclusive, i.e. greater than or equal to 0, and less than 8. Okay? We could implement that using this rather complex or overly complex structure, where we say if not, row is greater than equals to 0 and row is less than 8, and column is greater than equal to 0 and column is less than 8. If those two conditions are not true, we'll print out invalid square. But it's much more readable if we use temporary Boolean variables, like we store isValidRow equals, we assign to a new temporary Boolean variable isValidRow the result of the expression row is greater than or equal to 0 and row is less than 8. So isValidRow now stores whether or not that row is a legitimate value. And then we do the same for column, and we can subsequently say if not isValidRow and isValidColumn, we'll print out it's an invalid square. But we can probably make that better still by using De Morgan's rule to rewrite that as if not isValidRow or not isValidColumn, then it's an invalid square. So this is simply De Morgan's rule applied if not A or not B is equivalent to not A and B. Hopefully that's clear to you. As a general style rule with Boolean variables or functions, it's a good idea, as we did in the previous example, to name them something that makes it clear that they're Booleans, like isValid or isEndOfFile or canMove. These are clearly Boolean values. So is or can are good prefixes for Boolean values. Our fourth and final method for simplifying Boolean expressions and program structures is to use Boolean valued functions. So continuing our example of the chessboard, valid rows and columns, we could write a function that determines whether a particular coordinate is valid. It's in the range 0 through to 7 inclusive. So isValid returns true if the coordinate is a legitimate chessboard coordinate. So we return the truth of the coordinate is greater than or equal to 0 and the coordinate is less than 8. And now we can use that function in a simple if statement like if not isValidRow or not isValidColumn, print that it's an invalid square. Or we might think it's simpler, and I think it is simpler, to write the function as determining whether the row or column is invalid. So we can rewrite the function as isInvalid coordinate, return the true if the coordinate is in an invalid chessboard coordinate. So this time we'll return the truth of the coordinate is less than 0 or the coordinate is greater than or equal to 8. All of those would be invalid coordinates. And now we can write our expression very nicely, and I think most simply, as if isInvalidRow or isInvalidColumn will print invalid square. So there's a lot to take in there in terms of our ability to, the ability and methods that we can use to simplify our program logic. With experience, you'll get a lot better at it. So good luck. That's it for now. Thanks.